So this series of lectures, we're going to talk about the basic POD architecture, or proper orthogonal decomposition. It's based upon the singular value decomposition. And this is going to be sort of the introduction to thinking about selecting ideal basis sets for partial differential equations. So these set of lectures will be on the proper orthogonal decomposition. Okay? Or often what is known as the POD. All the POD is essentially finding an optimal basis representation of to expand a partial differential equation in. So we're going to start around that philosophy, build up some ideas from there, and just talk about basis selection and how we might go about doing something like that. So I always like to think about this in terms of a partial differential equation. So maybe something like of the form u of t equals n u. It could be a function of u, ux, uxx. These are all the derivative terms. Also a function x and t, and perhaps some parameter mu. And what I mean here by u is typically a vector. We're going to actually make it a vector in a moment, but these subscripts denote partial differential differentiation, and so forth. So what you have here is sort of the canonical model we want to think about, which is we have the time evolution of some quantity of interest u, and it depends upon some nonlinear function of u, as well as its derivatives, as well as time and space, and potentially some parameters in the problem. Okay? So this is going to be how we think about setting up what we want to do with this POD method, which is we want to solve this. And typically this might be some very high dimensional system. You might be solving a fluid flow problem, or thinking about solving atmospheric advection and diffusion, and you'd like to figure out how to be able to do something like this. As an example of an equation like this, a very specific one, let me write down for you this is something like the first and easiest nonlinear wave equation you could write down, which is ut plus ux. If this u here was constant, then this would just be a one-way wave equation. But now what we have is sort of a Burgers type term where the speed depends upon the amplitude. What ends up happening with an equation like this is you get the formation of shocks, or you can get that. And oftentimes what people do is add something like regularization term, and then now what you have here is Burgers equations. What it says is the time derivative of u plus u times ux, which is the first derivative, plus mu times uxx. So these terms here are diffusion. This term here is sort of a nonlinear advection term. So this is a representative of something like this, a very specific form. And of course, it's a continuous function u of both time and space. And what we do when we start thinking about solving these things numerically is we start thinking about the fact that actually what we're going to do is make a finite difference or a difference discretization of this partial differential equation. So we're going to take this continuous variable u and turn it into a finite dimensional representation of the infinite dimensional space. Okay? So that's going to be the whole idea behind solving partial differential equations in some simulation setting. So we think about needing to advance the solution forward in time and actually figure out how to take care of derivatives. So let me show you how we might do this in practice, because we want to figure out how to turn this infinite dimensional system into a large but finite dimensional system. So what we're going to do is think about taking u, which is a continuous variable of x and t, and we're going to turn it into a vector. Let's call this the vector u, which is going to be now evaluated at some discrete point x of n and time t. So at this point, we're just going to take care of discretizing the space variable x. Okay? In fact, we're going to call this u of n. So u of n is the solution u at the point x of n and time t. And here, n is going to be 1, 2, 3, all the way to n. So we're going to cut this up into n pieces. One way to think about this is to think about solving this on some domain, x, let's say from 0 to L, and I want to solve forward in time, and then I want to look at u, what it looks like in time. Okay, so this is our coordinate system. We might think about having some evolution of the system. For here, I just drew something like a pulse that might be moving forward in time. And so this is the continuous version. What essentially we do here is we're going to take this x domain, and we're going to chop it up into a number of finite points on a grid. Okay, so each one of these will be u of n, and the distance between the points will be delta x. So that's our discretization size, and this is our grid or our domain. And so what ends up happening when you do something like this is you take this infinite dimensional partial differential equation, and now you're going to turn it into a large finite set of differential equations. And in fact, the dimension of that's going to be given by n, which is our dimension of how we've basically chopped this up into a small set of points. Now, of course, here I've drawn it so it doesn't look very high dimensional, but you can imagine in many cases where maybe this is a two-dimensional, three-dimensional problem, and you want very high accuracy grids, then n is going to get exceptionally large. So that's going to be the idea of what we want to think about in doing a discretization from a differential equation to a partial differential equation. Okay, so now how do we think about taking something like this? We have the solution itself discretized. And by the way, we're also going to take steps in time, and there'll be some delta t associated with that. So we'll have space and time discretization. So we want to think about how we might handle the rest of this equation. In particular, one of the things we want to think about is the derivative terms. So let me take away this figure and think about the derivatives, because the solution depends upon the derivatives. For instance, if you have a heat equation, it depends on a second derivative. If you have a wave equation, I just showed you a simple version of it, it depends on one derivative. So how do you handle things like du dx? Well, what we do know, and in fact now we're really looking at what is the derivative of a specific point. And so now we can just go back to our first ideas of calculus to think about derivatives. And if I have a number of points that I'm cutting this thing up into, I can ask you something like, what is, in fact, du dx here at a certain point? Well, that's just the slope. So it's just a rise over run type formula. And so, in fact, you can use nearest neighbors. If I want to calculate the derivative at this point right here, then I could use its two neighboring points to approximate the derivative there, or the slope. In fact, that's a common thing to do. And these leads to these what are called finite difference formulas for derivatives. And in this case, a first derivative looks something like this. This derivative is equal to the point in front minus point behind over 2 delta x. So this is just rise over run. It's a slope formula. It's very simple. And so you notice what I've done is I've traded out this derivative for using neighboring points to compute it. Okay? So now what's going to happen in a system like this is that wherever I am, whatever u of n I'm at, it's going to depend upon its neighbors. So the entire n-dimensional system is coupled together just through the derivatives. The derivatives makes the systems talk to each other so that this n-dimensional system is all hooked together, for instance, by these derivatives. Okay? So that's a first derivative. And you can continue to do, you can either use more accurate derivative schemes, which I'm not going to talk about so much here. Those are fairly standard to come up with. But you can also think about, for instance, second derivative. The second derivative formula looks like this. So it's a point in front, point behind, minus twice the current point over delta x squared. And this is actually something very interesting, which is the higher the number of derivatives. So the first derivative gives you a delta x on the bottom. Second derivative gives you a delta x squared. Third derivative, delta x cubed, and so forth. In fact, this tends to lead what's called to numerical stiffness, because delta x is going to be very small. And so this is going to create quite large terms on top, potentially. And so you need to take smaller time steps to make sure to resolve these correctly. So at the end of the day, you've started off with something like this, some descriptive partial differential equation modeling your system. You've decided to discretize it. So you've taken this infinite dimensional spatial temporal system. You cut it down into specific points, x of n, and so you've got this thing u now defined at a finite number of points, in fact, n of them. You can approximate derivatives that would be in here very simply with these n points, and you have yourself a formula for moving forward into approximating this partial differential equation. And in fact, this partial differential equation now becomes a large, different system of differential equations. So what you find now is that it's no longer a partial derivative. It is a direct derivative of this thing. And this thing now is a function of un plus 1, potentially un plus 2, un plus or minus 1 plus or minus 2, x of n, t, and u. So that's the way we can start thinking about this, is what we've done is traded out a partial differential equation for a large system of differential equations. Okay? So this is going to be our basic idea behind the kind of problems we want to solve. So now the question is, how do we actually then go ahead and implement this? We know how to discretize now. We're going to turn this into a set of ODEs. So how do we actually go about solving this differential equation system? Okay, so one of the traditional methods in PDE theory is to use, it's called a separation of variables argument. And this is one of the first things that you typically tend to learn in the partial differential equations course, is how to do a separation of variables, because it's the easiest form of solution one might at least apply to the system, and you can see if it will work. So a system of differential equations like this, if you apply separation of variable argument, then what you're going to say is that u of x and t is a function of a of t, and make this a vector, times some matrix phi of x. Actually, I need to write these backwards. This will be a matrix, and this will be a function of t. So the idea behind separation of variables is to say I have x dependence and I have t dependence. I'm going to make the assumption that I can separate the x dependence from the t dependence and make it a product of these two different functions, one of time, one of space. And of course, there's a lot of systems you can't do this, but if you take enough variables, you can still get this right, as I'm going to show you in a little bit. But this is a standard method to try as a first solution type form that you might try in these PDE systems. It's the one you learned in the first bit of the partial differential equations class. Now what we're going to do here then is going to say, well, my solution U, this is typically my basis functions, and then their time dynamics. And the selection of the basis functions is what we're actually most interested in this reduced order model context. How do you pick out an appropriate set of basis functions? Okay? Because another way to represent this is in the vector form is uxt will be the sum of some coefficients a of n times those basis functions psi of n. Okay? So the trick here is to plug this formula into this equation and assume that I can, in fact, take a finite sum of basis functions and to try to discover their time dynamics so that I could actually, in fact, generate the time evolution through a numerical scheme. So let's go ahead and plug this in and see what we get. If you're going to take this thing here and basically I'm going to drop the indices from 1 to n. We're going to assume, of course, that whenever you see a sum, it goes from 1 to n. And we're going to go ahead and throw that in to this governing equation. So this is going to generate quite a few terms for us. And in fact, the nonlinearity is what kind of makes this thing fairly complicated. So remember here, what we're trying to do is we're going to say that U is a sum of A of n times C of n. But here now I have a time derivative, but the only thing that had a time derivative was my A. So that's my left-hand term. Is equal to, now you get quite a bit in this right-hand side. You know, it's a function of U, of the derivative of U. So only the psi of n is dependent upon x, so it takes up the derivatives. T, U. Okay? So that's what we have here, is we have a large sum on the left-hand side and a large sum on the right-hand side. And it's at this point that we want to start making some assumptions about the kind of basis functions we want to select. In particular, what we'd really like to do is we'd like to take a basis function set that are orthogonal to each other. In fact, orthonormal to each other. So what we'd like is the following property to hold. So this is either 0 or 1. It's 0 if n is not equal to m, and 1 if n is equal to m. So what this means is that the psi of n are, in fact, an orthonormal set of basis functions. And this is a standard thing, is you'd like to pick an orthonormal set to have this property because it makes your life quite simple afterwards, or simpler. Okay? And by the way, this is the inner product between two of these functions, which is defined as, if you're living on a finite domain here, from negative L to L, what it would mean is if I integrate from negative L to L, psi m star dx. That is the definition. And the star represents complex conjugation. So this is just a standard inner product space. And we're often used to this in vector form, where we think about two vectors being orthogonal, or even encoding things in an orthogonal system like this in a vector space, right? So these are all orthogonal directions, x, y, z. In function space, it's infinite dimensional, or at n dimensional if we want to chop this sum off at n modes. But there's n directions in this function space that are orthogonal to each other, and this is the condition for that orthogonality. Okay, so it's no different than what we're typically used to from vector spaces, but now we're applying these things on function spaces, and this is a standard definition. Okay, with that definition, you can then come back to this equation and multiply both sides by phi of m. See, this is n here, this is m here. Integrate from negative L to L. So that's what we're going to do on both sides. And what you're going to see what's going to happen is something very nice, which is when you multiply on this left-hand side, the phi of m, then you're going to have a phi of n times phi of m, which is going to be, and then we're going to integrate this. It's always going to be 0 unless what? Unless when that sum, when that n is equal to m, then it becomes 1. So everything is 0 except for that, and what's left over then at that point is dA of m dt. And is equal to, well, now we have to take this inner product of the nonlinear terms times psi of m. And so what this is going to give us is a large system of differential equations. Okay? So this is what we're after here, is now we can actually solve for the evolution of the A of m's. And this is going to give us now a system of differential equations to solve. So this is a standard, let's say, numerical scheme of how you might use a basis function set to derive for yourself differential equations, and then we can solve these forward using something like Runge-Kutta methods or any other scheme we might like to use in our system. Now, the goal in a reduced basis method, or at least in a reduced order modeling framework, is to trade out this very high dimensional n degree of freedom system, which is still the case here, which is there a way that if I pick the right basis functions, I wouldn't have to solve n differential equations, but maybe I can solve r differential equations where r is a lot less than m. Okay? And that's going to be the goal of reduced order modeling, is we're going to try to figure out how to do that and how to pick basis functions to do that. Okay? So these are modal expansion ideas, and I want to just represent for you one example of a function and how to think about representing any function in terms of a basis set. Okay, so that sets us up to start thinking about how to do this, how to construct for ourselves this basis set, and you can see that an optimal basis set could potentially be very helpful for us if we can get away with a smaller dimensionality than the n dimensions that we've picked here just by in this process of discretization. Okay, so reduced order modeling is all about this basis selection criteria and reducing the space in which you have to solve for these differential equations. So you're going to start off with a very large dimensional space. You can imagine if I discretize the airflow around a wing of an airplane wing, n would be tremendously large. And if I can actually make that dimension much smaller in some way, then you would like to do that. Okay, so what I decided to do is to give a little example. And I want to give you an example of, here, we're talking about trying to select out a great basis set. What I want to do now is actually come back a little bit and say, hey, let's just represent some kind of function in some basis set, and let's look at what happens to representation of functions in a basis set. And the basis set I want to pick are Fourier modes. Fourier modes, I can get to them very easily just by simply doing an FFT. So we're going to look at what it might look like to represent a function, in particular a Gaussian, in Fourier modes. So let me pull the computer over. And what I'm going to do is pull up my MATLAB here. Okay. And what we're going to do is program a little bit here. and talk a little bit about thinking about just representing something as simple as a Gaussian in Fourier modes. Okay? So let's start off with simple things first. Define a domain. Actually, I always like to start with that. Clear everything I've got. Now let's go ahead and define a domain. Size 20, I'm going to break it up into 80 points. Okay, so already just making this choice here, I'm going to pick a domain of size 20, break it up into 80 points. Okay, so that's my delta x is going to be defined by once I do this. And then what I'm going to do, since I'm using Fourier modes, I'm going to go ahead and define a linear space that goes from negative L over 2 to L over 2 in n plus 1 points, and x is simply the first 1 through n of those. Now the reason I did this is that normally when you're working with Fourier modes, it assumes periodic boundary conditions. So what I know is that if I'm going to go from negative 10 to 10, the negative 10th and the 10th point are the same. This is the periodic boundary condition. And so what I do is I want to go from negative L to L over 2 in n plus 1 points. The points I'm actually solving for are the first 1 through n, because the last point is the same as the first. I don't have to solve for it again. Okay? So the x I've defined here are my grid points. And these are the things I'm going to work with. So now let's just define a function on this domain. And here it's going to be, I'm going to define a parameter sigma, start it with 1, and I'm going to say that this thing is just simply a Gaussian. It's just a little bump. Okay? Let's go ahead and look at what this is. So plot x versus u. And let's plot this with a nice line width so that you can see it well on the screen. Okay, so I should be able to run this. And where is, yep. Okay, oops. Sorry. Let me get this here. All right. Why am I not running this? There we go. Let's call this POD test.m. Save. I'll run this. Okay, there it is. Simple, simple figure. So what we've got here is just a Gaussian I've plotted. There's 80 points that I discretized in, going from negative 10 to 10. Okay? Now what I'm going to do with this is I have this representation of it now in this, a finite difference did all the way across into 80 points. And what I'm going to think about doing is representing this in a Fourier domain, in a Fourier basis. And the Fourier basis are just simply cosines and sines. Okay? So of course this doesn't really look like a cosine and sine, but one of the fantastic results that Fourier gave us was that you could take any function and represent it in terms of cosines and sines. And of course you may need a lot of cosines and sines to do that, but you're guaranteed to be able to do it under certain conditions. And in fact, what we want to understand is how many sines and cosines does it take to represent a function like this. So let's go ahead and take this thing and start looking at it. In fact, what we'll do is we're going to do a couple things here. This is going to be a subplot. 2, 1, 2. Okay? So, or actually, we'll keep that plot there. And what we're going to do is do two things. We're going to plot it with a red circle. Let's do. Oops. I want to plot it with circles and lines. Okay, so we do both of those. But if I want the Fourier transform of this, I just say FFT U. That's it. And that was going to Fourier transform it, but now I'm in the Fourier domain. And one thing you know, if you've studied Fourier transforms, is the Fourier transform will take your signal, and due to the fast Fourier transform nature, it will shift the signal around and multiply every other one by -1. So we have to know if we're going to plot it in the wave number domain, which is the basis set for the Fouriers, then we have to get into this basis set and actually plot it appropriately. So now what we want are the wave numbers, which are going to be given by the following. And these are things like sine omega x. What the omega is, this is what these wave numbers are. Okay. So let me define these. Go from 0 to n over 2 minus 1, and then minus n over 2 to -1. Those are your k's. Okay. And what we're going to do now is make a subplot here. Guess I got to go to the end of this thing. Second subplot, we'll plot FFT shift of this k and an FFT shift of ut, absolute value of ut. And we'll plot that also in this form, line with 2. Okay, so let's run that. Oops. I did them both on, this is going to be there. All right, so here you are. The Fourier transform of a Gaussian is a Gaussian. So I went from here, and these are the discretization points. Remember, I chopped up 80 points. I have this Gaussian. It produces a Gaussian in the Fourier domain. And you can see now, hey, look, the Gaussian in the Fourier domain has quite a bit of number of points on it. And these now are Fourier modes. Now, what I want to show you is that when you look at this thing, what I've done here is I've picked a discretization of 80 points. And what you can see here is I don't maybe need all those 80 points. If I was going to represent this in a Fourier basis, I might need only half of those, maybe 40. But that's for this particular value of sigma. Come back over here, and if I look at this thing, and if I come back up here and just change the sigma, change it to 0.1, let me show you what this looks like. Oops. I should probably put the sigma right there. Very different now. In this case, here is a big fat Gaussian. So I took it from decay rate of 1 to 0.1, so it's much fatter. And now in the Fourier domain, look at this. I have 1, 2, 3, 4, 5, 6, 7. I could get a pretty good representation of this pulse here with 7 Fourier modes. Before, it took me about 40. Let me show you one other case here. Let me go the other way with this. Now I'm going to make a very narrow pulse. Now notice what happens. This Gaussian is very short in the time domain. It's got like 5 pulses or 5 discrete points that really characterize it very well. And then look how many Fourier modes I need. I need at least all 80 to actually get this right. Now this highlights one of the big problems. So first of all, it highlights a couple things. What you know about Fourier transforms is that they have this pairing, which is a very short pulse in time, or a very short spatial pulse, is in fact very broad in frequency. And if you have something very broad in time or space, it becomes very short in the frequency domain. Okay, so this is a property of Fourier transform pairs, which is delta function in time looks like a constant in the frequency domain. And if you have something that's constant in time, it looks like a delta function in the frequency domain. Okay? So this is one of the things. And this is also one of the challenges of thinking about representation. This little simple example tells you something about mode count. What was, in fact, the best basis function I should use? And you can see here, just by simply choosing different functions, it's not clear in this case that Fourier modes are very good representation. I need 80 modes to represent a simple bump. Okay? Whereas when I did have a very short, so very broad in the time domain, I could in fact use a small number of Fourier modes. So what this tells you a little bit about is the dimensionality. And in fact, Fourier modes are kind of common things to be using. And why do we like Fourier modes? Well, we like Fourier modes because we have some very nice convergence properties, and we can do the FFT in n log n speed. So it's very fast, it has spectral accuracy. So even though you might need a lot more Fourier modes than would be ideal, you can still do quite a bit with that. Okay? And this is sort of an illustration of that. So we can get in and out of the Fourier domain. And what we've essentially done, if you remember, what our goal is to think about this representation. U is some representation like this. I guess we can take this down now. And what we did here is we picked ourselves a Fourier basis. So these were oscillations. And by picking that Fourier basis, we can plug that in. And by the way, Fourier modes have nice orthogonality properties. So we plug this in. All we have to determine now is evolution for the A of nt. In the next lecture, we'll find out how to actually do this and solve a partial differential equation with this. Okay, so final comments. Well, let's continue this idea because really at the end of the day, once you have this format, there's actually a lot you can do with this. And in fact, people have done a lot with this. And there's a whole group of functions that came out sort of in the 1800s and 1900s called that now just go under the title special functions. And what these were different basis sets that you might use for different physical problems of interest. And a lot of these fell under Sturm-Liouville theory. And Sturm-Liouville theory basically tells you a little bit about problems that were self-adjoint, which in turn turned out to be quite a few coming out of quantum mechanics, electrodynamics. There were a lot of these types of problems with, given a certain boundary condition in dynamics, you could actually write them down as special functions, and they had this nice Sturm-Liouville property. And the Sturm-Liouville property told you a lot about these basis functions, in fact, being a complete set, so you could represent any function in terms of them. It also told you about orthogonality. It also told you about the fact that eigenvalues of these Sturm-Liouville operators were unique and ordered, and in fact real. And so in sort of the mathematical physics community, people were very interested in these, and they used them quite effectively, even for solving harder problems like this, where typically you would think about a linear problem. Linear problems are, in some sense, easier for us to solve because they're linear. So once I know the eigenvalues and the eigenfunctions of this operator L, I can solve the problem easily. And when I discretize it, the operator L just becomes a matrix. And if I know the eigenvalues and eigenvectors of a matrix L, and if it's self-adjoint especially, then I have the problem solved. And so a lot of mathematical physics, this L was a Sturm-Liouville form. And I put an epsilon in front of this n, which is when you try to solve harder problems. Back then, they didn't have the luxury of having what we have is very fast computers with things like MATLAB on them. What do you do with the nonlinearity? Because the nonlinearity is what complicates most of our solution techniques. Well, so what you do is you think about it as a perturbation. If it's small, then maybe what I can do is the leading order problem is dominated by the linear Sturm-Liouville problem. And then what I can do is come back and perturbatively add in the effect of the nonlinearity. At the end of the day, we're still trading out this problem for a problem with A of n's. And if we apply our orthogonality condition and do our expansion, we still are looking at this problem here. Dynamics of A of n, where we basically project the nth mode onto the psi of nth eigenfunction that would come out of this operator L. That's how we think about it from a perturbative point of view. And then we get ourselves a nonlinear differential equation system that we have to solve. But again, the hope is that this thing here, being n-dimensional, that there exists a basis set, psi of n, that might allow us, instead of taking a large n-dimensional system, that we could do something like a small r-dimensional truncation of the system. So this is going to be the basic concept that we're going to work with, and it's going to be all about how do you choose that basis set. That's what the POD method is all about, is how do I pick for a given problem what the ideal basis set is. Here, I've picked Fourier, or you could pick one of these, but that doesn't guarantee that it's optimal. And so what we want to talk about is how do you guarantee that's optimal.